Okay, this lecture and the next are really important because it's sort of consolidating the stuff we've earlier encountered on conditional probability. And you're going to be working more exercises starting with these last two homeworks. The reason it's important is the bulk of the first midterm, which is coming up quite quickly. Take a look at the syllabus. The bulk of it is on conditional probability, which is equivalent to using this thing called Bayes' rule. It's conditional probability, but with an uglier equation. But the equation actually, what it does is it helps you solve these things. And really, all it translates down to is if you do the diagram correctly, and then you formulate your probability question correctly, and then use Bayes, you're just reading off the pieces of the diagram that translate directly into those pieces for Bayes. Okay, so pay careful attention to this because again, the bulk of the first exam is going to be on Bayes or conditional probability. So here's the rule. The rule is ugly. It says given hypothesis H and evidence E, but it could be give A, given B, but we're just going to use this language of H and E. I'll explain that later. So this is the probability of H given E equals this ugly thing, okay? What this all translates down to essentially is this is one top branch of the diagram, and this is that same branch plus the other branch. If that sounds vaguely familiar, it should because you've already done this with previous conditional probabilities. Bayes, I should mention, a bit of historical background. He was a reverend. He did a lot of things. Interesting fellow, but he came up with this formulation for calculating probability. And you might think this stuff looks totally irrelevant. It's just calculation. It's math. You're doing this to get rid of your math requirement. How is this applied anywhere? In this computer day and age, with data, with Google, with searches, with social media, Bayes underlies all of that. It is like the driver. As one computer scientist put it, who's very much aware of what's in the tech field, he says if you had to put a number on it, maybe 90 to 99% of all the computer algorithms that are being run out there that you rely upon for your everyday platforms, your phones, your apps, and all of that, your internet searches, it's all basically Bayes. So this stuff looks artificial, but it's already running loose in the world. We're going to be talking about more its conceptual structure. Okay, what Bayes is saying, what it really is, it's just a more explicit way of thinking about conditional probability and the diagrams. So, as I said previously, the numerator is one branch of the tree. The denominator, the thing on the bottom you're dividing by, adds the total number of branches. So let's go back to our standard canonical problem, urns with balls. Recall this one? So remember once again, there's two urns, and there's a problem like this exactly on the midterm. Just as a heads up, you either get heads or tails. I change it very slightly, but essentially the content's the same. If you draw from urn 1, there are 3 reds, 1 green. So the chances of getting 2 reds breaks down to you draw from urn 1, you get red. Or the other way you can get 2 reds is you draw from urn 2, and you get a red and a red. All Bayes is saying in that ugly formula is it's breaking down each component of the branches. It's saying the top branch, this times that, divided by the same branch plus that times that times that, the other branch. Conceptually, graphically, that's all that ugly equation is saying, okay? When you map it more directly, it's probability of urn 1 given that you got 2 reds. So that's the probability of urn 1 times the probability of red from urn 1 times the probability of red from urn 1 divided by that same thing plus the other branch. The way Bayes lays it out is it's the probability of that first thing, and then you flip around that expression. So it's RR given urn 1 divided by that same exact expression right here, plus the opposite, probability of not urn 1 times the probability of, and you flip it around again, RR given, not divide, given, not earn 1. Okay, that sounds ugly, that sounds complex. It's actually not. It just looks complex. Here's how you memorize the equation. So here's the way you memorize Bayes' rule. You're going to have to know this for the midterm, not just in terms of applying it, but I ask you straight up in the axiom section, the rules or axiom section to give me basis formula. The reason I asked you for that is simple. You're going to have to use it in the test. So it's the first, so probably of H times, you flip it around, probably of E given H divided by the same thing plus, similar to what you did up here, but now the opposite, not H, and then you flip it around. Not H given E. If we make it more concrete, instead of just H and E, since we've been using A and B, the probability of A given B results in the first, which is the probability of A, times the flip, the probability of, so not A given B, but B given A, times the same thing, I have it color coordinated to show you the matching, plus the opposite. So that would be not A given B. So not A and the flip, B given not A. Here's how you, if you see that matching, good. Here's how you memorize it. It's the first times the flip divided by the same plus not first, and then you flip that same thing, okay? The way you get this down is not just through straight up memorization. That helps, but you're going to have to practice, practice, practice. So again, the homeworks and the practice are crucial. If there are more branches, you get the generalized Bayes rule. The book has all this fancy notation. There's this sigma notation. If you've taken pre-calc, some of you may have. You've probably seen this before. It's sigma, which just means sum over the branches. It's the same as Bayes. It's just more branches. Don't worry about it. Okay, so that's it for the lecture. Focus on the upcoming homeworks because they're the crucial practice that's going to get you ready for the exams. Pay special attention from here on out to these problems. They'll get you ready. See you next time.